Hello, Calculus. I hope everything's going well for you guys. And this is going to be the video over antiderivatives of natural logs. But before we do that, I just want to do a quick refresher on finding the derivatives, or the regular derivatives of natural logs. Now remember the rule. We first got to take within the parentheses and derive it. So in other words, derive. And then, once you have that, you'll then divide it by the original. So let's go ahead and do that. So for the top, we're going to take the derivative of 3x to the 7th. Multiply the 7 to the front, you get 21. And then you are to subtract 1 from the power. So you should get x to the 6. And then once you have that, you divide by the original. And the original was 3x to the 7th. So 3x to the 7th. So there you basically have your answer, but you can still simplify. The 21 divided by 3 will give you 7 on top. And if you look at x to the 6th and x to the 7th, you can take away 6 x's from each one. Take away 6 x's from that, it's go away. Take 6 x's from this, and you have 1 x left over on bottom. So that simplifies down to 7 over x. Okay, that's what you learned last week. You learned how to derive natural logarithms. But now, here's the question I want to ask you. What if I give you this? What if I give you the derivative and I want you to give me what the original was? Or in other words, if I gave you 7x, how would you find what the regular or the original function looked like? And that is what's going to be our objective today. We're basically going to give you the derivative, and I need you to anti-derive to find the original function. And that is what today's objective is to find the antiderivative and get you back to natural logs. So, let me explain how this is done. I don't know why I had this slide. It's really pointless. Anyway, so let me give you an example. Let's say I give you the integral 2a divided by a squared dA, or da. A little humor. But anyway, so here is the trick for deriving these. And the trick is, I want you to first look at the bottom. And the bottom in this case is a squared. And then what I want you to do is I want you to derive a squared. And of course, if you derive a squared, you're going to get 2a. And now, the derivative is 2a. I want you to check to see if 2a is on top. Or in other words, if you derive the bottom, and if it ends up, the derivative of the bottom ends up being on top, then that allows you to take this function and rewrite it like this. Or in other words, what you can do is take this and rewrite it as its original natural log function. Or you take the natural log of the bottom plus c. So in this case, we already checked. We derived the bottom, which was 2a, and that turned out to be what was on top. So in other words, we can rewrite that as its natural log of the bottom. And in this case, the bottom would be a squared. And there you go. That would be the antiderivative. Basically just doing the reverse of what we did last week. Now, some of you are probably wondering, Ms. Shulin, is there a reason why you have absolute value bars here? How come you're not using just regular parentheses? Good question. Good question you're thinking about. The reason why I'm putting absolute value bars around this example is just to make sure that our number stays positive. Because watch. What would happen if, say, I took the natural log of -1? For those of you who have a calculator with you, go ahead and type that in. I'm going to go ahead and type it in real quick. Natural log of -1. And this is what my calculator says. Domain error. So in other words, natural log doesn't work if it's negative. And that's why we use absolute value bars, just to make sure that no matter what number we have, we keep it positive. Because that's what absolute value bars do. They keep numbers positive. So just want to clarify that for all these examples, we will be using absolute value bars, just so we don't run into this issue. And now, before I continue, I want to show you a neat trick. If you're concerned about if you got the right answer or not, you can actually check. And let me show you how. To check, you literally just have to derive the answer that you got. Derive natural log of a squared. And of course, you know how to do the regular derivative. Remember, you derive the inside, which will give you 2a, and then you divide by the original, which is a squared. And check it out. That matches what you got from the beginning. So you know you got the answer right. You know that this has to be the antiderivative. That is definitely a neat trick, and I strongly recommend that you use that. You use that checking ability, especially for a future quiz that may be coming up. Don't worry, it'll be open note. All right, so moving on. Now let's do an actual example. Oh, sorry. So just basically a synopsis of what we're talking about, or what we're going to be looking at today. Mostly our objective is we're always going to look at the bottom, and then we're going to derive it. And if the bottom derivative, or if the derivative of the bottom matches what we have on top, then we are free to just say natural log of the bottom. And we would say that would be our answer. Of course, make sure you put the absolute values, and you also put plus c. You always use plus c for any any indefinite integral. All right, so let's just do some practice problems so you can get comfortable with it. So for this example, first things first, let's take a look at the bottom. Take the bottom and derive it. And if you derive it, the derivative of x is 1. The derivative of plus 5 is just 0. You don't need the 0, so the derivative is 1. Check the top. Does the derivative of this match the top? Sure does. So that makes your life easy. You just got to say that the answer is natural log plus c, and inside the absolute value bars, you put the bottom, which will be x plus 5. Done. Piece of cake. And of course, if you want to check, you know what to do. To check your answer, you first take what you got, derive it. Derivative of x plus 5 is 1, and then put the original on bottom. And if that matches what you started with, then you know you got it. Done. Okay, I think you guys know how to check from here on out, so I'm just going to go ahead and continue from here and just write the answers down. All right, so for that one, we got it. Now this one. Let's take a look at the bottom. Let's derive it. The derivative of 3x cubed, 3 times 3 is 9, and then it's going to be x squared, plus 7, the derivative is 0. So we just need 9x squared. Does it match the top? It sure does. So we know we can just write the answer as the natural log, plus c. Again, use absolute value bars, and what goes inside the absolute value bars is the bottom. So 3x cubed plus 7. Whoop, done. And of course, you can check that if you want. Checking's really easy. And then the third example, it's going to be very similar. You're going to derive the bottom. You'll find out that it matches the top. So you can just rewrite it as natural log of the bottom, x squared plus 1 plus c. You guys can check that one on your own, but it's literally the same as the other two. Okay, you're probably thinking, okay, Ms. Shulin, this is actually pretty easy. What's the catch? What's the catch? Why is this so easy, Ms. Shulin? Are we going to have a case where it doesn't match the top? Is what some of you are probably asking. And it turns out there will be some cases where that does happen. For example, let's say we have this example. Let's look at the bottom and let's derive it. And of course, the derivative of x is just 1. And 1 does not match the top. Darn it, Miss Shulin, what am I supposed to do now? It turns out when you have a case like this, or a simple case like this, there is an actual easy way to rewrite it so it's easier for us. For example, we derived the bottom, and the bottom was 1. Now, if only we had 1 on top instead of 2. Well, out of curiosity for now, what if I take the 2, and for now, I rewrite it as 2 times 1? For now, you guys know that is true because 2 times 1 does equal 2. But why would I rewrite it like that? The reason why is, what if I kept the 1 where the fraction is, and then what if I took the 2 and brought it to the front? You guys remember from previous examples that we are allowed to do that. We're allowed to take factors or numbers being multiplied and bring it to the front. So instead, I can rewrite this as 2 being the front, and then the integral of 1, because the 1 stayed behind, and then over x dx. Now let's see what that does for our problem. Well, now that it's rewritten like this, let's try again. Let's derive the bottom. The bottom is 1. Does that match the top? It does now. Whoop, whoop. So now that we have that the derivative of the bottom matches the top, we can now rewrite this as natural log of the bottom, which is x, plus c. But then what do I do with the 2? If you guys remember from previous examples, that 2 just comes down and b's in the front. So it's 2 times natural log of x plus c. Or just 2 natural log absolute value of x plus c. Same thing. So yes, you are allowed to do that. Oh, excuse me. Anyway, so for those examples, that does work. And of course, it would make your lives a lot easier for you to recognize that. So now, take a look at these examples. So you take the bottom, derive it, you'll end up getting 1. And does that match the top? It does not. But never fear. We can rewrite it so that the top is 1. Rewrite 5 as 5 times 1. And then the 5 can go to the front. We'll leave the 1 with the fraction. And that will give us 5 in front. And then on the other side of the integral, the 1 will stay with the fraction, x on bottom, dx. All right, now that it's rewritten like this, let's try again. We will derive the bottom. Derivative of x is just 1. Does that match the top? Sure does. So you can take this, rewrite it as just natural log of the bottom, which is x, plus c. Now what do we do with this 5? Leave it in the front. And there you go. Piece of cake. For the second one, you guys can probably recognize it's literally identical to the previous one, just this time it's going to be a 9. You guys can do the work with if you want, but again, you will see that the answer will just be 9 times natural log of x plus c. All right, piece of cake. I gotta get a drink of water real quick. Okay, I'm good. Now the next example, brace yourselves. Oop, yep, come on. We got trig. Oh boy, Miss Shulin. But gotta do it still. So, as always, we gotta take the bottom and derive it. Now, maybe this will be a good time to bring up the Polston procedure to help us remember what the derivative of cosecant is. So, remember we have tangent, secant, secant. Arrows going this way. And then we're going to have cotangent, negative, cosecant, cosecant. And remember, the way that this works is that you first got to look at which trig function you want to derive. In this case, we want to derive cosecant. So to derive cosecant, follow the arrow. So if we follow the arrow, we're going to have to do negative cosecant times cotangent. So negative cosecant times cotangent is going to be the derivative. So let's write that, negative cosecant cotangent. And does that match the top? It's so close. We got the cosecant and the cotangent. We just don't have the negative. Darn it. Shoot. If I just had a negative in the front, I'd be good to go. Piece of cake. I wonder if I can rewrite it somehow so that I do have a negative in the front. Well, let's try something. How about for now, I'm going to put the invisible 1 in front. So 1 times cosecant times cotangent, which really doesn't change anything. It's still cosecant cotangent. But now, what if I take this 1 and rewrite it as the multiplication of 2 negative 1s? Double check. Negative 1 times negative 1 is the positive invisible 1. So you know we can do that. And then everything else, the cosecant x, cotangent x, all over cosecant x, that didn't change. Okay, Miss Shulin, cool. We took the invisible 1, rewrote it as negative 1 times negative 1. Cool. So what does that do again? Am I going to do something similar to the previous examples where we'll take one of these negatives, put it in the front? Oh. I think you guys are catching on. But yes, let's try that. Let's take one of these negative numbers, bring them to the front. So we got a negative 1 in front of the integral. And then let's keep this negative 1 in the front here. So negative 1 times cosecant times cotangent all over cosecant. And negative 1 times cosecant cotangent, doesn't that match what we want? We want negative 1 or negative cosecant cotangent. And that's exactly what we got. Because if you derive the bottom, as from the Polston procedure, that's negative cosecant x cotangent x. And the negative 1, if you multiply that to the negative cosecant, that just becomes, well, negative cosecant. Exactly what we want for the top. Boom. So then, now that we have that, we can rewrite this as natural log. And what do we put in the absolute value bars of the natural log? The bottom. So CSC absolute parentheses x. But remember, we're not done yet. We still got this negative 1 in the front, and that will stay in the front. So negative 1 times natural log cosecant plus 3. Or if you actually multiply that, that just becomes negative natural log cosecant x plus c. And there you go. That trick is extremely handy for these examples, so keep that in mind. All right, so that was just an introduction to finding antiderivatives. This was the first assignment for this video. I'm going to go ahead and continue. I'm going to go ahead and finish the rest of the video, and then show you the second assignment, and then you can finish those 2 assignments at your convenience and make sure they're turned in before the due date. All right, so let's begin. For the rest of the video, I need to refresh you on this type of example. So let's say we need to find the integral of this. Some of you are probably tempted to say, oh, for this, we can use the orange peel rule. Here's the thing. The orange peel rule you use to derive. We are not deriving. We are doing the antiderivative. So you can't really do the orange peel. We have to do the reverse of the orange peel. And the reverse of the orange peel is U substitution. So, it's been a couple weeks since we've done U substitution, so this is a refresher. For U substitution, I want you to take what's inside the parentheses and set that equal to U. So in other words, that'll be x squared plus 1. And then what's going to happen is I'm going to derive the right side and the left side. If I derive this side, or the right side, x squared will become 2x. Derivative of 1 is just 0. So I'm going to label that as dx, or in other words, this is the derivative of the x side. On the left side, if I derive the u will be 1. And of course, I'll label the 1 as du, saying that du is the derivative of 1. And of course, 1 times du is just du. So you don't have to keep that 1 there. So in other words, we got what we need. And now let's do some substituting to help us derive this problem. So I still got the integral. I still got the parentheses squared. But the x squared plus 1 we labeled as u. So I'm going to replace that with the u on the inside. And then the 2x dx, check it out, that matches what we have over here. So I can replace all of this with du. And that's exactly what I'm going to do. Replace it all with du. So now that's rewritten this way, you just have to derive u squared. Or not derive, you have to do the anti of u squared. So you know how to do the antiderivative. You first add 1 to the new power to get u cubed. Then you divide by that new power, which means you'll divide by 3. And then, of course, you do plus c. And once you're there, you basically have the answer. It's just that we need to get rid of the u now. We don't need the u anymore. And, well, what did we say the u was? X squared plus 1. So replace the u with x squared plus 1, and there's your answer. X squared plus 1 all cubed, all divided by 3. And if you wish, you can rewrite that as 1/3 times x squared plus 1 cubed plus c. Either one of these answers is acceptable. Now, the reason why I had to refresh U substitution with you guys is because there will be some examples of finding the antiderivative of natural logs that we will need to use U substitution for. For example, let's say I have 4 minus 2x. And, of course, I gotta find the antiderivative, so let's use that natural log trick. First, I'm gonna derive the bottom. The derivative of 4 is just 0. Ain't nobody tell me nothing. Okay, and then we gotta derive negative 2x, which is gonna be negative 2. Don't say positive 2, it's negative 2 because of that minus sign. And of course, that's the derivative of the bottom. Does that match the top? It does not. All right, Ms. Shulin, I can just go ahead and find two numbers that multiply to 1, where one of them is negative 2. Some of you may be able to figure this out. Some of you may not. But just to be safe, let's say that maybe we should try something different. Because finding two numbers that multiply to 1 may be hard for some people to figure out. So, we're going to have to try and do something different. What we're going to have to do instead is use substitution. Now, what I want to be u is the bottom. For these examples, always make the bottom part the u. So u will be 4 minus 2x. Now derive the right side and the left side. If you derive the right side, again, derivative 4 is 0. Derivative of negative 2x is negative 2, not positive 2. And then label that as dx. On this side, the derivative of u is just 1. And then, of course, label that as du. Derivative of u is on the left, derivative of x is on the right. I'm going to keep that 1 there, actually, for now. Now, real quick, you probably recognize that this equation has negative 2 dx. We don't have a negative 2 dx. We just have a regular normal dx, which means I got to get rid of this negative 2. And since the negative 2 is being multiplied, the opposite is to divide. So I'm going to divide that to both sides. So that's going to leave me with 1 for negative 1/2 du, all equal to dx. All right, now that we've got that situated, let's go ahead and plug some stuff in. So I kept the integral, and I didn't do anything to the 1, so I'm going to leave the 1 as it is. The bottom, however, the 4 minus x squared, I labeled as u. So I'm going to go ahead and replace that with u. And then the dx, we already got that labeled. Dx is the same thing as negative 1/2 du. So that's what I'm going to replace it with. I'm going to replace the dx with negative 1/2 du. All right, and if you want to make this look a little bit prettier, you can go ahead and take this negative 1/2 and you can bring that to the front. So negative 1/2 integral 1 over u and then just du. Okay, so now that's rewritten like this, let's see if we can do our little trick now. So in other words, take the bottom, derive it. Well, you know the derivative of x is 1. The derivative of u, still a variable, should be the same thing. The derivative of u should just be 1. And does that match the top? Sure does. So now we can use our natural log. Natural log of the bottom, where the bottom is u, and then plus c. But what do I do with the 1/2? Well, you guessed it. That just stays in the front, just where we put it. And now we're 98% done. Because remember, once we get the anti, we don't need that u anymore. So we're going to have to replace the u with what it was originally. And what was it originally? Let's scroll back up. 4 minus 2x. That was what u was. So I'm going to replace the u with 4 minus 2x. And voila, there is your antiderivative. And of course, if you want to check it, you know exactly what needs to be done to check it. Here's the one thing you'll have to keep in mind, though. The negative 1/2 will still be in the front. So if we check, we'll have to keep the negative 1/2 in the front. Let's derive the top. Derivative of the top, derivative 4 is 0. The derivative of negative 2x is negative 2. And then divide by the original. And the original would be 4 minus 2x. Well, to start off, we know a negative times a negative, that's going to make that plus positive. And also, if you check, the 2's, top and bottom, those can cancel out. So then you're just left with the 1 on top and the 4 minus 2x on bottom. All right, and let's check. Let's see, does that match what we started with? We started with 1, 4 minus 2x, 1 all over 4 minus 2x. All right, so that's how you check those examples. We're good to go. We know that we got the right answer. Boom, 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 done. Okay, so with that said, I want you guys to try this one on your own. This one is literally the same thing as the previous one, just a little bit different. Treat it the exact same way. Go ahead, pause the video and try this one now. Okay, you should have resumed the video by now. If you want to check your answer should be 1/5 in the front, and then natural log of the bottom, which will be 5x plus 2 plus c. And of course, if you check it, you'll end up getting exactly what you started with at the very beginning. But I'm not going to work through it. I'm going to work through a different example instead, one that you probably need a little bit more exposure to. But if you have any questions about this example, feel free to email me or rewatch the video. Or if you want to do Google Hangouts, we can do that too. I am here to help. But let's go to the next video. Or not the next video, the next slide. The next slide has a different example that I really need to talk about. So let's say we approach this like we normally would. We would look at the bottom and we would derive it. And if we derive the bottom, derivative of x cubed would be 3x squared. Derivative of 2 is just 0, so just 3x squared. And look at the top. Well, we got the x squared, we just don't have the 3. And of course, this means I probably need to use substitution. Because, I can assume there's a 1 here, and some of you may not recognize what will multiply to get 1, so that we can help out with 3. But anyway, so now let's try u substitution. As always, for u substitution, you want to put the bottom as u. All right, let's derive the right side and the left side. If you derive the right, that'll be 3x squared. Label that as dx. Derive the left side, derivative of u is 1, and then label that as du. Now, some of you are probably wondering, yeah, I got dx. I don't have the 3, and I don't have an x squared here. I have it up here, but it's not with the dx. How is that going to work? Now, funny you asked that. Let me show you something. So, for now, I'm going to take the x squared and rewrite it as 1 times x squared dx. And of course, you guys can see that 1 times x squared would still give you x squared. So this is technically correct. But now here's what's going to happen. I'm going to keep the 1 on top of the fraction. And then the x squared, I will move it. But I won't move it to the front. I'm actually going to move it over to the side. So it becomes x squared multiplied by dx. And you are allowed to do that. You are allowed to take the x squared and multiply it with the dx. Because technically, as long as it doesn't go on bottom with the x cubed plus 2, it is technically correct. The more you know. And the reason why I do that is because it'll make our lives much easier. Because, well, if this is x squared dx, I have x squared dx in the blue part. I just have to get rid of that 3. And I'm going to get rid of that 3 by division. So that's going to become, over here, 1 cubed du. And then on the right side, x squared dx. All right, so now let's use this information to make our integral easier to anti-derive. All right, so this is what I got so far. I'm going to keep the 1 as 1, but on bottom, the x cubed plus 2, I labeled as u. So I'm going to change that to u. And then the x squared dx, that's the same thing as what we got here. So I'm going to replace that with 1/3 du. So this will now become 1/3 du. And now it looks very similar to problems we've done in the past. And if you want to make it easier, you can go ahead and take the 1/3, bring it to the front. So now we'll have 1/3 integral of 1 over u du. Okay, 3 does not look right. There we go. Now that's rewritten like this, let's try our little tactic again. Let's derive the bottom. Of course, the derivative of u is just like the derivative of x. It's just going to be 1. Does that 1 match the top? Sure does. So that means I can rewrite it as a natural log. The natural log of the bottom, where currently the bottom is u, and then plus c. And then the 1/3 gets to stay in the front with everyone else. And of course, we're only 98% done because we cannot leave our final answer as u. We need to go back to its original state. And the original u was 3x cubed plus 2. So put in x cubed plus 2, and you have your answer. And again, if you need to check that, you know how to check it. Derive the x cubed plus 2 divided by the original. Make sure you multiply by the 1/3 in the front, and you'll find out it will give you what you started with. So, you know you got your answer. All right. So now, I want you to try this one on your own. I do want to mention real quick, this is a common error kids make. I will tell you, you will have to use u substitution. So u equals 7 minus x to the 4th. If you derive the right side, the derivative of 7 will be 0, but then when you derive this, it's going to be negative x4 cubed dx. A lot of you kids will totally forget about that negative and just do 4x cubed and not put it negative. That negative or minus in the front is very important. So I just wanted to point that out. Go ahead, do the rest from there. This one is very similar to the one you just did. Go ahead, try it now. Okay, you should have resumed the video by now. If you want to check your answer should be negative 1/4. Natural log, absolute value bars of the bottom. 7 minus x to the 4th, and then plus c. You see why that negative in the front was very important. If you had forgotten about it, you would have had positive 1/4, and, well, that would have made the whole question wrong. So, now, with that said, I believe I only have one more example to show you, and then we'll be done for this lesson. And the next one is kind of a doozy, so just brace yourselves. I need a drink of water. Whoops. Okay, I'm good. Last slide. Here we go. So, evaluate the integrals using u substitution. Oh, dear Lord, Miss Schulentz. Woo, okay. I guess I'll start with what I normally start with. I'll take the bottom and derive. And if I derive the bottom, 2x cubed, that should derive to 6x squared. 2x squared, that'll derive to 4x. And the derivative of 2x is just 2. And does that match the bottom? Does that match the top? Of course it doesn't. Of course it doesn't, Miss Schulin. Sorry, I'm just repeating what you're probably thinking. But anyway. So yeah, the derivative of the bottom does not match the top. That means I probably got to do u substitution. So as before, I got to take the bottom, label it as u. And make it give it a little more space. So u equals the bottom, where the bottom is 2x cubed plus 2x squared plus 2x. Okay. Now I got to derive the left and the right. If I derive the right side, it should be 6x squared plus 4x plus 2. and label that as dx. And then on this side, derivative of u is just 1, and then label that as du. All right, Miss Schulin, I know I am probably going to have to rewrite this somehow so that it matches the top. Or probably what I should do before I go any further is I should probably do this. I'm going to take the top and rewrite it as this times 1. And what's going to happen is the 1 will stay on top of the fraction. The 2x cubed plus 2x plus 2x on bottom will stay. The x, this part, the 3x squared plus 2x plus 1, I'm going to put that with the dx. So that's going to be 3x squared plus 2x plus 1 dx. Okay? Yeah, I probably need to write that a little bit lower. So I'm going to move that down, going to move this down, going to move this down, move this down. Okay, just to make a little bit more room. Okay, so I apparently need to get this part to look like this. How in the world am I going to do that? How am I going to do that? Is what you're probably thinking. Oh, shoot. Okay. Now, my recommendation is it looks like they look almost the same. It just looks like the bigger one was just multiplied by 2. Wait a minute. I wonder, could I take out a GCF? Let's look. What's the biggest number I can divide all of these by without going over? And it looks like I can divide all of these by 2. And what about the x's? Yeah, they don't all have an x, so I can't take out an x. So my GCF is 2. So then what would that mean for the rest of my problem? I would just have to divide everything by my GCF of 2. And what will that get me? The first one, 6 divided by 2, will give me 3x squared. The 4 divided by 2 will give me 2x. And the 2 divided by 2 will give me 1. Oh my gosh! I have the dx's and I have the 3x squared plus 2x plus 1. Yay! So that basically means all I have to do is just divide by this 2. Oh, shoot. I'm not going to do that. I just have to divide by this 2 to both sides. So then off to the side, okay, I'm just going to go ahead and bring this down again. Oh, shoot. Bring this down. Bring this. Stop that. Bring this down. Bring this down. Just to make room. I'm sorry if this is messing you guys up. I sincerely apologize. So then, up here, I should have 1/2 du equals all of this. 3x squared plus 2x plus 1 times dx. Finally, I got everything I need to start the substitution part. So let's do it. The 1, we didn't do anything to 1. The 1 stays on top. This part is what we labeled as u. So we will change all of that on bottom. It's just u. And then the 3x squared plus 2x plus 1 dx matches this. So I can replace that with 1/2 du. So let's go ahead and replace that with 1/2 du. Oh my gosh, Miss Schulin, it looks so much more pretty right now. I can finally have an easy problem to work with. I understand. I understand. We can go ahead and move that 1/2 to the front. So we get 1/u du. And then the rest is easy from here. If you derive the bottom using our natural log trick, if you derive the bottom, derivative of u is 1. That matches the top. So we can write down our answer. Our answer will be natural log of u plus c, and the 1/2 goes to the front. And then, of course, last but not least, we got to replace the natural log, we got to replace the u with its original. And the original was 2x cubed plus 2x squared plus 2x. So write that in the absolute value bars. 2x cubed plus 2x. I don't have enough space. 2x squared plus 2x. Absolute value bars plus c. So that one, a little bit tricky. You still got to use the same stuff we've done before, just had to use a GCF. Because the GCF from here, from this spot, would help us match what we need to match to get the du in. And with that, you guys know how to do antiderivatives of natural logs. And with that said, you are now ready to go and do the 2 assignments. I don't know when I'll have the due date, but I will let you know 47 is a bonus if you want some extra points. And with that said, if you have any questions, email me, or if you want to do Google Hangouts, you just let me know. And you have yourselves a lovely day.